Good morning, all. Am I audible? Please let me know in the comment section. I hope you all can hear me. Am I audible? Please let me know. I hope I'm audible. Okay. Let us start the next beautiful subject. It's called analog electronics. Right? So let me start the next subject, analog electronics. Okay. Let us quickly revise all the basic things that you need to remember in analog electronics. First, let me go from the basics. First, let us discuss about semiconductor devices. Some basics. I cannot revise all the things. In semiconductor physics, what are all the basic things that you need to keep it in your mind? That things I will discuss now. So first of all, in semiconductor physics, you should remember about the energy band diagram. In energy band diagram, how will you draw the energy band diagram first of all? Energy band diagram is drawn between band energy versus length, length of the band, right? So that is length versus band energy. So if I'll draw the band energy band diagram, how it will become? There are three regions, right? So let me break it. Region number 1, region number 2, region number 3. So in region number 1, this region number 1 is called valence band. Region number 2 is called forbidden energy gap. That is energy gap between two bands, right? So that is energy gap. Region number 3 is conduction band. Usually electrons will go from where? Valency band to conduction band. When we are applying external voltage or internal voltage variations due to temperature, whatever, generally electrons will be tightly bounded in valency band. So due to some external or internal parameter changes, electrons will be getting released from here and it will go to conduction band. That is how that process will occur. Now here the voltage, energy voltage that is available in up to energy valence band is EV we are defining. Up to the energy that is required up to reach this level, let me define it as EC. Now then what is the energy that is required in order to cross this gap? That will become EC minus EV. That's all. That is energy required in the band. That is the amount of energy that is required to break this energy gap in order to push the electrons to go from valency band to conduction band. Okay, I hope you all are very clear. There are two regions now. One is valency band, another one is conduction band. Before conduction, generally in all material, electrons will be in valency band. நீங்க ஃபோர்ஸ் கொடுத்த உடனே என்ன ஆகும் அப்படின்னா எலக்ட்ரான்ஸ் வந்து வேலன்சி பேண்ட்ல இருந்து கண்டக்ஷனுக்கு போகும். நடுவில் ஒரு கேப் இருக்கும். அந்த கேப்பை நீங்க பிரேக் பண்ணி தான் இங்க கண்டக்ஷன் பேண்டுக்கு போக முடியும். அதுக்காக நீங்க எவ்வளவு அமௌண்ட் ஆஃப் எனர்ஜி வந்து ஸ்பெண்ட் பண்றீங்க டு கோ ஃப்ரம் வேலன்சி பேண்ட் டு கண்டக்ஷன் பேண்ட் பை கிராசிங் திஸ் எனர்ஜி பேண்ட். That is called EC minus EV, amount of energy that is required. Okay, I hope you are getting me. Next, let me discuss about some basics. In this semiconductor physics, actually we are taking, in order to design our analog electronic devices, we are taking two materials. One is germanium and another one is silicon. Now when we are designing germanium and silicon, in order to break, if you go with the germanium நம்ம எடுத்துக்கிட்டோம் அப்படின்னா it will demand 0.7 voltage cutoff in order to break this region. In order to go from valency band to conduction band, silicon will demand 0.7 voltage, germanium will demand 0.3 voltages. Okay, I know many of you guys will know these things. Next, this semiconductor material generally will be classified into three types. Let me define all these things. We all know generally we are having three types of materials. What are those? One is insulator, and second one is conductor, and third one is semiconductor. Generally we have this three type of material, right, in our universe. Here insulator means conduction current will be completely zero. Ideally I am speaking, resistance offered by the insulator will approach infinity. So according to Ohm's law, if you apply I is equal to V by R, when resistance will approach infinity, 1 by infinity will become 0 ampere. So insulator generally having ideal case it will be infinity. Practical case its resistance will be in mega ohm, very high, or I can say its value is very high. So the current is in microampere or in nanoampere, almost that is equal to 0 in case of insulator. When we go for conductor, ideally I am speaking conductor will carry infinite amount of current and resistance offered by the conductor will become 0 ohm. That is general, but that is ideal actually, not general. This is ideal case. When we go for practical circuit, what will happen in practical circuit? If you take the practical circuit, the resistance offered by the practical conductor is very low. When resistance will be very low, what about current I is equal to V by R? It will be when the value of the denominator is very low, automatically what will happen? Numerator will become very high. So what we can say is conductor will carry huge amount of current, insulator will carry zero amount of current, practically we can say. Okay, now when we go for semiconductor, let us see the behavior of semiconductor once. So how semiconductor will conduct? Semi name itself we are calling it as semiconductor. It will partially conduct, partially won't conduct. It means what? If you take our diode, we all know the general property of diode. How this diode will work? In case if you draw the waveform of the diode, voltage versus current, when our diode will turn on in first region, we have to continuously increase the voltage. When the voltage level will goes to greater than 0.7, suddenly what will happen? Diode will break down and it will allow enormous amount of current. So partially it won't conduct, partially it will conduct. These type of materials are simply called semiconductor devices. So semiconductor devices means in general they will partially conduct, partially won't conduct. So now in order to design our analog electronic devices, we are going to give priority for semiconductor devices. We are going to travel along with the semiconductor devices. Let us discuss about the classification of the semiconductor devices. If you go along with the classification, generally semiconductor devices will be classified into two types. One is pure semiconductor, and another one is impure semiconductor. If you again break impure semiconductor into two types, one is called N-type material and another one is P-type material. So we all know we are going to design our analog electronic devices with the help of impure semiconductor materials. Actually, what do you mean by impurity and purity? Pure semiconductor material means there will be no composition. நம்ம வேற எந்த மெட்டீரியல்ஸையும் வந்து இது கூட நம்ம ஆட் பண்ண மாட்டோம். லைக் இப்போ நம்ம கோல்ட் எல்லாம் எடுத்துக்கிட்டோம் அப்படின்னா, நம்ம இப்போ இந்த செயின் எல்லாம் செய்யறாங்க இல்லையா, செயின், ரிங்ஸ், வாட் எவர் தி ஜுவல்ஸ், இன் ஆர்டர் டு டிசைன் தி ஜுவல்ஸ், gold will be added with some other materials. That is called impurity. So if you want to achieve, இப்போ நம்ம ஒரு டிவைஸ் வந்து நம்ம மேனுஃபேக்சர் பண்ணணும் அப்படின்னா ஜஸ்ட் வந்து பியூர் செமிகண்டக்டர் வச்சு நம்மளால பண்ண முடியாது. So it will be combined, it will be some other materials வந்து இது கூட combine பண்ணி தான் we are designing the materials. So we are going up with the impurity, that is called extrinsic material. We are calling it as extrinsic materials, and this is called what? Intrinsic material. This is called intrinsic material. Anyway, we are using extrinsic material only, and it will be classified into two types. One is P type and another one is N type of material. Next, remaining things you have to capture, guys. This is revision class, I cannot teach all these things. Okay, kindly go through your lectures once. Now in our semiconductor device, basically you should learn about some basic things. Basic things means we saw there are two bands, right? One is valence band and another one is conduction band. One is valence band and another one is conduction band. I hope you all have remember. Now when we take valency band, so let me define. In valency band, the concentration of holes will be defined as P naught. Concentration அப்படின்னா எவ்வளோ number of positive charge carriers வந்து valency bandல இருக்கு, that is called P naught. Similarly, let us discuss about conduction band. Conduction band வந்து நம்ம யார் எடுப்போம் அப்படின்னா N naught. N naught அப்படின்னா மீனிங் என்ன அப்படின்னா, that is concentration of electrons in conduction band. That is எவ்வளோ electrons வந்து conduction bandல இருக்கா, எவ்வளோ holes வந்து valency band la irukka. Actually what will happen, energy band la when the electrons are going from valency band to conduction band, இப்போ இந்த இடத்துல ஒரு பிளேஸ் இருக்கு, இங்க இருக்க எலக்ட்ரான் வந்து என்ன ஆகுது அப்படின்னா இங்க இருந்து ஷிஃப்ட் ஆயிட்டு கண்டக்ஷன் பேண்டுக்கு போகுது. அப்ப என்ன ஆகும், that vacancy will be considered as holes. That vacancy will be considered as holes. So in valency band generally we will have holes. Why? Because the electrons that were placed in the valency band will be shifted from valency band to conduction band. True sir, 100% true. So the conclusion is, if you multiply the value of n naught with the p naught, it will be equal to ni square, whereas ni is denotes the intrinsic concentration. This is intrinsic material மொத்தமா எவ்வளவு கான்சன்ட்ரேஷன் இருக்கு, எவ்வளவு சார்ஜஸ் வந்து கிரேட் ஆயிருக்கு உள்ள, that is called intrinsic concentration at the given temperature, at the given temperature. So this law, this formula, இத வந்து டிஃபைன், this law இதுக்கு பேர் என்ன அப்படின்னா, that is called mass action law. We are calling it as mass action law. So mass action, we are taking a bulky action. We are shifting huge amount of electrons suddenly from valency band to conduction band in order to let the material to conduct. If நம்ம semiconductor devices la enna agum, I already clearly defined, right? So when we go along with the semiconductor materials, so there are three regions, that is region number 1, region number 3. So generally in semiconductor materials we know up to, so let us take, we have silicon device. In case of silicon, up to 0.7 what will happen, our device won't conduct. After 0.7 suddenly it will conduct and a huge amount of current will flow through the diode. So you have to understand, so what will happen, bulky action will be taken after 0.7, immediately huge amount of electrons will be shifted from valency band to conduction band. Okay, so these are the some of the basics. Next we need to talk about mobility of the materials. Mobility of the materials. Mobility means it is the drift velocity for unit electric field. So mobility is the drift velocity for unit of electric field. It will be represented by mu. So whereas Vd denotes drift velocity. Vd denotes drift velocity, and E we all know, that is called electric field. That will be considered as electric field. So this is the formula to calculate the mobility of the material. So first of all, what do you mean by mobility? It is how fast electrons are traveling from one point to another point. Charge வந்து generally, let me take charge, that will be better. So mobility அப்படிங்கிறது ability of a charge to fastly to move from one point to another point. So mobility அப்படின்னா என்ன, ஒரு சார்ஜ் வந்து எவ்வளவு ஃபாஸ்டா வந்து மூவ் ஆகுது ஒரு பாயிண்ட்ல இருந்து இன்னொரு பாயிண்ட்க்கு, அத பத்தி பேசுறது தான் mobility. Okay, that will be defined as Vd by U. We all know. Yes. Next we need to discuss about drift current. So anyone please tell me what is the formula to calculate the value of drift current? Let me calculate the drift current. Drift current will be denoted by Id, and this can be represented by Id equal to N A Q into Vd. So that is the general formula to obtain the value of drift current. Now here this will be further defined as N A Q mu into how, sir? Just now we saw mobility can be defined as drift velocity divided by electric field. From this, drift velocity can be defined as mu into E. So kindly revise your lecture. Already I have been defined all these things, right? Nothing I am giving new. Everything is already clearly defined. So you can go through the lecture once in order to get the complete idea about the things that I am defining here. Okay. Next, let me define the drift current density. So here we know that is N denotes the concentration, A denotes the area, Q denotes the charge. Don't think too much. Nothing is there. So this is the formula to obtain drift current. Now let us see the formula to obtain the value of drift current density. So let me discuss about drift current density. Let us discuss about drift current density. It will be represented by J. So J is equal to drift current per unit area. Okay, that's all. So this can be further defined as drift current. We know mu A Q. Just now I have been defined that value, right? Sorry guys, this is N. Sorry, forgive me. N into E. Okay, don't get confusion. I made a small mistake. Let me correct it. So actually this is what? This is N, right? So what will get? N A Q mu E upon A. So A getting cancelled. Finally, what will get? N, Q, mu, E. So that is the formula to obtain the value of J. Yes, sir. And I hope you all have remember in electromagnetic theory, I have defined a formula to obtain the value of current density J. வெளியில இருந்து வந்தவங்களுக்கு அது தெரிஞ்சிருக்கும். So J is equal to sigma into E. If you just compare this formula with this formula, what you are getting? See there, J equal to sigma into E. So what it denotes clearly, sigma equal to N Q mu. Yes, sir. So from this, what we are getting here, clearly this is conductivity. Sigma denotes the conductivity. Sigma is called conductivity. So conductivity will be defined as NQ mu. So let me generally define this. Conductivity will be defined as NQ mu. That is true, sir. But here when we go for two materials, or நம்ம general நம்ம semiconductor devices வச்சு நம்ம என்ன design பண்ண போறோம்? Let us take, suppose I am designing diode. How will you design the diode? I need two materials. One is N material, another one is P material. So N material, mobility of N material will be mu N, mobility of P material will be mu P. What is the net mobility? Mu N plus mu P. So net mobility will be defined as mu N plus mu P. So this formula can be rewritten as mu N plus mu P into N into Q. So that is the formula to obtain the net conductivity of semiconductor material. I hope you all are getting me what I am trying to conclude. Okay. Yes, sir. So apart from that, there are few more things to understand in case of semiconductor devices, that is diffusion and drift current. So let me define the diffusion and the diffusion current, right? So let me define the diffusion current density, right? So you have to, in diffusion and drift current, what you need to know is diffusion current density. That is the most important formula that you need to keep it in your mind. So let me define it. One second. Yes. So diffusion current density, diffusion current density due to electrons and holes in a material. First of all, I'm requesting you to kindly go through the lecture, because this is revision class. Revision class means I can just recapture. I cannot bring everything. How come, when come, where come, these things. For these questions, you should go through the complete lecture, right? Okay, sir. So diffusion current density can be defined as Jn equal to Q dn into dn by dx. Okay, sir. Similarly, Jp equal to minus Q into dp into dp by dx. What is this? So here, first of all, J denotes the current density. Jn denotes the current density due to electrons. Jp denotes the current density due to holes. First difference. Next, Dn denotes the electron diffusion coefficient. Electron diffusion coefficient. This is electron diffusion coefficient. Similarly, dp denotes what? Holes diffusion coefficient. Then dn divided by dx is what? Electron concentration gradient. That will be defined as electron concentration gradient. Next, dp by dx is what? Hole concentration gradient. Hole concentration gradient. Hole concentration gradient. That's all. Just do remember, rest of things you know, no? This is charge, positive charge, negative charge, positive charges, right? That is Q, 1.609 into 10 power minus 19 is its value. That's all. Next, let us discuss about the formula to calculate the length of the diffusion. Length of the diffusion. Okay, fine, sir. How to calculate the length of the diffusion? That is L is equal to square root of D into tau, whereas L denotes the length of diffusion. Length of diffusion. L denotes the length of diffusion. Similarly, D denotes the diffusion constant of charge carrier. That is diffusion constant. That is diffusion constant of charge carriers, diffusion constant of charge carriers. Similarly, tau denotes the lifetime, that is carrier lifetime, charge carrier lifetime, how long it will carry the charge. So that is the charge carrier lifetime. Okay, I hope you all are getting it. Next, this diffusion constant d is there na? இது நம்ம வேற எப்படி டிஃபைன் பண்ணலாம் அப்படின்னா it is actually the product of thermal voltage and mobility of the charge. Vt stands for thermal voltage. Vt stands for thermal voltage, and mu we know that is mobility. If you just substitute this d into this formula, this into L, what will you get? L is equal to square root of d will be replaced by Vt into mu into tau. We can also rewrite this expression like this. Okay. Next, suppose if they are asking to calculate the diffusion length of electrons, then they will give you the value of dn into tau. So dn means what? That is a diffusion constant charge carrier, but for electrons. Similarly, if they are talking about holes, find out the diffusion length of the holes means square root of dp. You can also consider tau p if you want. That is lifetime of positive charge carrier and lifetime of negative charge carrier. That is tau n. Okay, forgive me. That's all. So these are the things that you need to remember. Okay, when we are in semiconductor devices, right? So these are very important things. Okay, let us move on to the next part, that is called diodes. Okay, we will take diode and let us see the characteristics of p-n junction diodes. First of all, the first term that you need to learn here is about potential. Learn about potential. That is, we are calling it as built-in potential. That is the actual name for this. Some people will call it as contact potential. There will be one more name for this. Some people. So it will also be considered as contact potential. That is cut-in voltage. Don't think too much. This is called cut-in voltage. That is amount of voltage that will be required to turn on the diode. இப்போ நம்ம டயோடுக்கு என்ன பண்ணுவோம், 0.7 voltage silicon, 0.3 voltage germanium எல்லாம் போடுறோம் இல்லையா. ஆக்சுவலா அந்த வேல்யூ வந்து எப்படி கால்குலேட் பண்ணாங்க அப்படின்னா, let me define the formula. That will be k into t upon q into ln of na divided by na into n divided by ni square. Kindly go through the lecture. நம்ம கிளாஸ் அட்டெண்ட் பண்ண எல்லாருக்கும் தெரியும், நான் இது எல்லாத்தையுமே கிளியரா டிஃபைன் பண்ணியிருக்கேன். So here this will become, that is cut-in voltage. We are calling it as V gamma. So that is contact potential or built-in potential or cut-in voltage. And then K denotes the Boltzmann constant. Boltzmann constant. That is Boltzmann constant. Okay, and it has some value. That value will be approximately, let me define, 1.38 into 10 power minus 23 joules per Kelvin. So we can define it as J by K. That is K. And then we all know Q will be defined as electron charge. That value is 1.609 into 10 power minus 19 coulomb. And T denotes the temperature. And Na means what? Concentration of acceptor in P side. That is concentration of acceptor. Kindly go through the lecture. Okay. Nd means what? That is concentration of donor, negative charges. Ni is what? Intrinsic concentration at a given temperature. Okay, these things are very important, just to keep it in your mind. Next, this is cut-in voltage. Another one is most important formula. You should remember the formula to calculate the diode current. Our next target, diode current id is equal to I naught s, that is reverse saturation current, into e power v upon n times of vt minus 1. Okay, and let me define it as vd. That will be better. Now here let me define all these things. This id, that is what? Diode current. We all know this will be considered as diode current. What about this ios? That is called reverse current, right? So that is diode reverse current. That will be given in an exam. Diode reverse current. Next, this vd stands what? Diode voltage. Vd stands what? Diode voltage. Vd stands diode voltage. What about this eta, sir? That is ideality factor. That value should be 1 for germanium and it will be 2 for silicon. Guys, one more thing. In your examination, 98% they won't give this value. இந்த வேல்யூ கொடுக்க மாட்டாங்க. ஆனா அவங்க என்ன பண்ணிருப்பாங்கன்னா சிலிக்கான் டயோட வச்சு நான் டிசைன் பண்றேன்னு சொல்லிருப்பாங்க. ஒரே விஷயம் மைண்ட்ல வச்சுக்கோங்க. By default in your examination, if they don't talk about this value, bracketல வந்து eta equal to 2 அப்படின்னு அவங்க கொடுக்கல அப்படின்னா சிலிக்கானா இருந்தாலும் நீங்க என்ன பண்ணிக்கணும், வேல்யூ வந்து 1 தான் வச்சு நீங்க ப்ரொசீட் பண்ணணும். Anyway, that value is 2 for silicon. I'm not denying that. But in your examination, right, question takers won't think about these values at all. They will only talk about diode current. In such a case, you no need to consider eta by 2 or 1, which material that they are using, silicon irka, germanium irka, yara use pannirukanga, evlo value or nothing is required when there will be no data. So conclusion enna, data ve illana eta oda value 1. Data kuduthirundha kuduthirukka value eduthu potukonga avladha. Don't think too much. Okay, and then T denotes the temperature in Kelvin. Okay, sorry, where is VT actually, that is thermal voltage. Let me define. VT is thermal voltage. Okay, that's all. Now I hope you all know this basics, right? Apart from that, when we go with the diode, நம்ம diode வந்து ஃபோக்கஸ் பண்ணோம் அப்படின்னா diode நம்ம நிறைய ஈக்குவலன்ட் சர்க்யூட்லாம் வரைஞ்சிருப்போம். இப்போ diode வந்து என்ன கேட்பாங்க அப்படின்னா first you will be requested to calculate the static resistance of the diode. எக்ஸாம்ல டைரக்டா क्वेश्चन கேட்பாங்க, find the static resistance of the diode அப்படின்னு கேட்பாங்க. How will you calculate? Static resistance means that is DC resistance. Let me call it as DC resistance. So RDC will be simply calculated with the help of voltage drop across the diode divided by current flow through the diode. That's all. Simply DC voltage drop across the diode and current flow through the diode. That is static resistance. So static resistance அப்படினாலே DC resistance தான். Just you can remember. Okay, next அடுத்து என்ன கேட்பாங்க அப்படின்னா question number 2, dynamic resistance அப்படின்னு கேட்பாங்க. Dynamic resistance usually நம்ம எங்க calculate பண்ணோம் அப்படின்னா it will be in AC. So dynamic resistance will be simply considered as RAC, that is AC resistance. How to calculate the AC resistance? Dynamic resistance வந்து you can calculate from the slope actually. ரெசிஸ்டருக்கு வந்து நம்ம characteristics slope வரைஞ்சிருப்போம், அந்த ஸ்லோப்ல இருந்து நீங்க calculate பண்ணணும். So RAC will be equal to 1 by reciprocal of the slope. So slope na enna? Slope means voltage versus current only. Don't think too much. That is voltage versus current slope. So from that slope, if you calculate the value of dV by di, that is slope value, that will give you the value of, that is slope actually, that is slope. So from this, sorry guys, 1 minute, actually we need to consider the current here, right? 1 minute. Let me draw the graph again. Don't get confused. I am just going up with some other characters. That is wrong. In diode, current should be in y-axis, voltage should be in x-axis. So, if slope வந்து என்ன வரும் அப்படின்னா di by dt தான் வரும் உங்களுக்கு, right? If slope is di by dt, resistance generally it is the product, it is the ratio of voltage and current, right? So, அப்போ voltage resistance என்ன வரணும், dv by di ன்னு வரணும். So, both are opposite to each other. That's why AC resistance is reciprocal of the slope value. When slope value will be directly given, you can directly calculate this value. Okay, and you can also calculate this AC resistance with the help of N into beta T divided by IF. What is this? That is very simple. Beta T, thermal voltage, eta, ideality factor. If it is given, example கொடுத்திருக்காங்க அதோட value 1, 2, 3 அப்படின்னா அதை substitute பண்ணிக்கோங்க. கொடுக்கலனா அதோட value 1. And this is forward bias current. IF na current through the diode in forward bias. அது என்ன current through the diode in forward bias? Forward bias ல போற current actually நம்ம எப்படி calculate பண்ணுவோம் அப்படின்னா, see, நம்ம டயோடுக்கு ஒரு current பார்த்தோம் இல்லையா, ID equal to I0S into e power VD upon eta times of VT minus 1. இது அப்படியே extend பண்ணீங்கன்னா it can be written as IOS into e power VD upon eta times of VT minus IOS ன்னு வரும், கரெக்டா? So this is called forward current and this current is called reverse current. That is the total current actually. So it will be the combination of forward current and reverse current. இந்த reverse current அப்படின்னா என்ன? So IR equal to minus IOS. Forward current அப்படின்னா, that is forward current equal to IOS into e power VD upon eta times of VT. So that is the formula to calculate the forward current. I have defined here. So this forward current is this one only. This is the formula to obtain the forward current. Okay. This is all about resistance. Now let us discuss about the capacitance of the diode. Next important area is capacitance of the diode. When you focus the capacitors, first let me discuss about Storage capacitance, that is the first one. Let us discuss about storage capacitance. Okay, sometimes in your examination, in place of storage they will use diffusion capacitance. Actually that is diffusion capacitance only, so it can also be considered as diffusion capacitance. What is the formula? Diffusion capacitance can be calculated with the help of Q upon, let me define it, tau into, okay, let me define in terms of okay, eta into Vt. So here Q we know that is charge divided by eta ideality factor, Vt that is a thermal voltage. That's all. So that is how we are calculating the value of diffusion capacitance. This diffusion capacitance is always directly proportional to square root of doping of the material. It is always directly proportional to doping of the material. So doping of the material அப்படின்னா எவ்வளோ கான்சன்ட்ரேஷன்ல இருக்கு மெட்டீரியலோ, டோப்பிங் அப்படின்னா கான்சன்ட்ரேஷன். டோப் பண்ணுவோம் இல்லையா, ஒரு என் மெட்டீரியல் எடுத்துக்கிட்டு அதில் எலக்ட்ரான்ஸ் வந்து கம்மியாக இருந்ததுன்னா மோர் எலக்ட்ரான்ஸ் அதுக்குள்ள டோப் பண்ணுறது, மோர் சார்ஜஸ் வந்து டோப் பண்ணுறது, தட் இஸ் கால்டு டோப்பிங் ப்ராசஸ். If you don't understand this word, read in Google somewhere, understand it. Okay, I know you all know this, I'm just telling. Next let us discuss about the second capacitor. Second capacitance is what? That is transition capacitance. Next let us revise transition capacitance. Next property, transition capacitance. So transition capacitance means that is Ct, which is equal to epsilon naught epsilon r a divided by Wd. Here Wd means that is width of the depletion layer, width of the depletion layer while calculating transition capacitance. And rest of things we know, that is area, epsilon naught epsilon r, we know that is relative permittivity and permittivity of free space, everything we know. And this width is directly proportional to reverse bias voltage. So from this what I can say is transition capacitance is inversely proportional to reverse voltage. See there, if I will replace it by VR, this all people will become constant, they won't vary. So I can simply say Ct is inversely proportional to reverse bias voltage. Very important relation. So there will be a n in the power, you can consider, that is step graded. There are two type of grading actually during manufacturing. Anyway, you don't get the question from that, I will just define. Actually அது என்ன பண்ணுவாங்க அப்படின்னா, manufacturing point of view you can find in textbook, it will be written like this. இந்த n அப்படிங்கிறது என்ன அப்படின்னா, material design ல வந்து we are using two type of grading. One is step grading, another one is linear grading, Step grading அப்படின்னா என்னோட வேல்யூ வந்து 1/2, that is fixed. Linear grading னா என்னோட வேல்யூ வந்து 1/3. Okay, anyway, this is not required, I'm just recapturing. If you want to learn this basics, you can just keep it in your mind. Okay, fine sir. So these are all the some of the basics of the diodes. I have defined all these things. Okay, let us focus at the next material, that is called our bipolar junction transistor, BJT. Let us keep our attention with the bipolar junction transistor. So when we go along with the BJT, we all know it will be classified into two types. One is PNP, another one is NPN transistor. Yes. How will you represent the practical representation of NPN transistor and PNP transistor? NPN transistor. Let me draw the structure of NPN transistor. It will be drawn like this. Yes sir. So this is collector current will come here, this is base current will come here, and then this is emitter region, current will go like this. Correct sir. So here emitter current will be equal to addition of collector current plus base current. That is the general representation. And here collector terminal, emitter terminal, base terminal. This is for NPN transistor. How will you draw the PNP transistor? Same way, just in PNP transistor we have to reverse the direction of the current. Through collector we are sending the current, through base we are sending the current, again through emitter current will enter. Once again here also this relation will be remain same. IE is equal to IB plus IC. There will be no changes in the current, right, in both material. Again it will be collector, this is emitter, this is base. There is no changes in the basics. Correct sir? Yes. Now you can see in BJT configuration, we can see there are many type of common configuration, common base configuration, common emitter configuration, common collector configuration. So understanding those things are little bit important. I know you all know these basics. Let me just recapture it once. So when we go for common base configuration, common emitter configuration, common collector configuration, what is the input and what is the output? Input and output. Let us recapture those basics once. Can you please tell me what is the input in case of common base configuration? In common base configuration, emitter is the input, collector is the output. Am I right, sir? Yes. Common emitter configuration. In common emitter configuration, base will be the input, collector is the output. In common collector configuration, common collector base will be the input, emitter will be the output. So you can just remember like this. See there, common collector வரும்போது மட்டும் இங்க என்ன ஆகுது அப்படின்னா emitter. In general, output remaining caseலலாம் யார் இருக்கா? Collector தான் output. You can fix it except common collector. அப்ப common collector வரும்போது மட்டும் collectorக்கு பதிலா emitter replace பண்ணிடுங்க. இங்க ஆட்டோமேட்டிக்கா see by default இப்போ நீங்க காமன் பேஸ் கான்ஃபிகரேஷன்லயோ காமன் எமிட்டர்லயோ இப்போ நமக்கு அவுட்புட் என்ன வந்துடும்? அவுட்புட் எப்பயுமே கலெக்டர் அப்படிங்கிறது ஈஸியா ஞாபகம் வந்துடும். அவுட்புட் கலெக்டர்னா பை டிஃபால்ட் இன்னும் ஒரு டெர்மினல் தான் இருக்கு. அந்த டெர்மினல் இஸ் கோயிங் டு பி தி இன்புட். டோன்ட் கெட் கன்ஃபியூஷன். ஜஸ்ட் டு ரிமெம்பர் திஸ் திங்ஸ் பிகாஸ் some one more question you can expect in state government exams in IES at all. In gate they won't test you with a small logic, they will test your intelligence. Anyway, I can't give assurity, they may be taken question from this basics also. So just to remember, let us discuss about the next most important region, that is called mode of operation. Very important. So mode of operation. Yes sir. So mode of operation, let me go to next page. Let us discuss about quickly mode of operation. Okay, so in mode of operation we have to understand how to deal with the different modes. So let us take our transistor once again. For transistor la mottama ethana terminal iruka? 3 terminals. First let me take emitter base junction. We will discuss about junctions first. நம்ம transistor la suppose let me have collector, emitter and a base. So it has 2 junctions, right? Junction number 1, junction number 2. So if you take this one, junction number 1, that is common base junction, collector base junction, sorry. This junction is emitter base junction. Correct sir. So based on the configuration we have different types of different diodes on the different methods on the connect பண்ணிருப்போம். correct? Okay, just that is leave that things. Coming back to the basics. So when we go with the emitter base junction and collector base junction, first let us take for collector base junction எடுத்துக்கிட்டு emitter base junction எடுத்துக்கிட்டு, let me say emitter base junction forward bias ல இருக்கு sir, forward bias. collector base junction forward bias ல இருக்கு. அப்ப transistor வந்து என்னவா act ஆகும்? Transistor will simply act as a switch. In this case transistor will simply act as a switch. True sir, when both are in forward bias. Switch அது என்ன ஸ்டேட்ல இருக்கும்? switch வந்து on stateல இருக்கும். Transistor will act as a switch and it will be in on state. Second thing, when both emitter base junction and collector base junction are in forward bias, then its internal resistance is very low. It has very low value of the internal resistance. Very low value of the internal resistance. That is the first case. Okay, so when both are in forward bias, then this will be, call it as saturation region. We are calling it as saturation region. First one is over. Let us moving on to the second one. So once again let me take emitter base junction, collector base junction. Let me make both as reverse bias. When both are in reverse bias, both emitter base junction, collector base junction are in reverse bias, in that case also again it will act as a switch. Yes sir, but in this case state of the switch is off state, and if you go along with the internal resistance, that will be very high value of internal resistance. Okay, when both are in reverse, this region is called what? We all know that is called cutoff region. Yes sir. So let us moving on to the third one. So I think I have taken EAB first, CB second. Right, sir. Next one is, suppose take emitter base junction is in forward bias. Emitter base junction is in forward bias. Collector base junction is in reverse bias. Collector base junction is reverse bias. I hope you all know this is called what? Amplifier. This action is called amplifier. Actually, what we are doing with the help of transistor? Transistor can act as a power booster. Transistor can act as a power booster. That's why transistor will be considered as an active element because it will boost the power. When it will boost the power? When it will act as an amplifier, in that case it will boost the power. So transistor will be acting as a effective power booster when it will be operated in amplifier region. So this is the best region where transistor will be mostly preferable to operate. So இங்க தான் வந்து டிரான்சிஸ்டருக்கு வந்து அதிகமா priority கொடுத்து ஆப்ரேட் பண்ண வைப்பாங்க. ஏன்னா இங்க தான் பவர் வந்து அது பூஸ்ட் பண்ணும். That is the important region we are calling it as. And this region will be simply we are calling it as active region. So transistor will be operated in active region. Most important thing. Okay. ஒரு டிரான்சிஸ்டர் வந்து நார்மலா வந்து நம்ம எந்த ஒரு டிவைஸ்ல கனெக்ட் பண்ணாலும் அது வந்து ஆக்டிவ் ரீஜன்ல தான் இருக்கும். சரி, அப்ப அந்த சேச்சுரேஷன் ரீஜன் அப்புறம் இந்த கட் ஆஃப் ரீஜன்லாம் பார்த்தாலே அப்பெல்லாம் நம்ம என்ன பண்ணுவோம், அதெல்லாம் வந்து டிரான்சிஸ்டர் வந்து நீங்க எந்த இடத்துல சுவிட்சா யூஸ் பண்ண ட்ரை பண்றீங்களோ அங்க நீங்க அதை யூஸ் பண்ணிக்கலாம். ஆன் ஸ்டேட் ஆஃப் ஸ்டேட் மட்டும் தேவை அப்படின்னா இன் தட் கேசஸ் யூ கேன் கிவ் priority to the transistor to let it act as a switch. Last case, sir, emitter base junction will become reverse bias. This is reverse bias, and collector base will become forward bias. This is reverse, that is forward bias. Then what will happen? It will act as a attenuator. But in the case நம்ம யூஸ் பண்ணவே மாட்டோம், mostly இதை பத்தி நம்ம பேச மாட்டோம். So I'm just giving, this is very poor transistor action. Power on the output reduce ஆயிடும், that is not required actually, right? So this region we are calling it as reverse active region. What is the name? That is called reverse active region. அதுக்காக இதை நம்ம எங்கேயுமே யூஸ் பண்றது இல்லை அப்படின்னா நான் சொல்ல மாட்டேன். We are using it in digital electronic circuit. Logic families are there, na? There is a separate chapter is called logic families. In logic families, in order to design the logical circuits, in some cases priority will be given for reverse active region also. But it is rare to use in practice, but in some places we are using it. Okay, I hope you all are getting it because I have been completed all the basics. Okay, let me define few more relations about the transistor current and voltage at all. We know generally emitter current will be the addition of base current plus collector current. That is practice. In practice we will use. ஆனா இது கூட ஆக்சுவலா என்ன வரும் அப்படின்னா there will be one more current will be always considered with this, that is called ICBO. இது யார் அப்படின்னா கலெக்டருக்கும் பேஸுக்கு நடுவில் இருக்க லீக்கேஜ் கரண்ட், that is collector to base leakage current, that will be considered as collector to base leakage current. That is how we are generally defining. But what will happen is we are not அதோட significant effect வந்து அதிகமா practical circuitல இருக்காது. அதனால இது approximate என்ன பண்ணிடுவாங்கன்னா it will be equal to IB plus IC னு சொல்லிடுவாங்க. That's why we are following this one. Actual relation is this one. Emitter current will be the sum of IB plus IC plus ICBO, that is collector to base leakage current will be added with this one. Next, in the base current, next let me define the first factor is called current amplification factor, that is called alpha. I hope you all know this. Current amplification factor அப்படினா that is the ratio between collector current and emitter current, that is called current amplification factor, or we can simply what, IC is equal to alpha times of IE. You all know this one. Basically we are defining these terms at all places. Similarly, this is what, current amplification factor. There will be one more term, that is called base current amplification factor. Base current amplification factor, that will be defined by beta. So beta எப்படி நம்ம define பண்ணோம் அப்படின்னா beta is equal to IC by IB. So from this what we can say, we all know IC is equal to beta times of IB. That is the another relation. This is called base current amplification factor. Anyway, both are considered as what, amplification factor only. I hope you all know the relation between alpha and beta. alpha equal to what? Beta upon 1 plus beta. That is the relation between alpha and beta. Okay, sir. So let us discuss about a few more expressions. Next, this collector current is there, na? IC. IC நம்ம ஜெனரலா இப்ப எப்படி டிஃபைன் பண்ணுவோம்? Just now we saw IC can be defined as alpha times of IE. But நம்ம practiceல உள்ள பார்த்தோம் அப்படின்னா கேர்ஃபுல்லா நம்ம டிவைஸ் அப்சர்வ் பண்ணோம் அப்படின்னா it will carry one more current, that is called what? ICBO will be flowing through here also. So collector current will be the sum of alpha times of IE plus collector to base leakage current. That is how we are generally defining it as. Okay. Okay, sir. Similarly, when we are defining it in terms of IE, ICBO will come into the picture. Suppose, let me take the same collector current. When I am talking about base current, IB பத்தி நம்ம பேசிட்டு இருந்தோம் அப்படின்னா, with this we will have one more current, that is called ICEO. What is this? Collector to emitter leakage current. Okay, so this formula is very important. This formula is very important because most of the times you can expect the question. Let me define it one more time. So IC can be defined as beta times of IB plus, with this we will consider collector to emitter leakage current ICO also. First thing, but here we know the relation IC is equal to what? Alpha times of IE. Just now we saw, right? IC can be defined as alpha times of IE. Similarly, if I will define the value of ICEO, collector to emitter leakage current, that will become 1 plus beta times of, approximately, that will become 1 plus beta times of ICBO, collector to base leakage current. That is the relation between collector to emitter leakage current and collector to base leakage current. If I substitute this value into the above expression, you will get collector current can be written as beta times of IB plus 1 plus beta times of collector to base leakage current ICBO. Most important formula. Okay, and please do remember this expression. Whatever the things that I am giving, I know intentionally I am giving something based on your examination. Examla enna கேட்பாங்க அப்படிங்கிறது எனக்கு தெரியும். That's why I am keeping my concentration that much in these areas. So kindly understand the process. Okay, I hope you all are getting me what I am trying to conclude. So this is for collector current. Similarly, if you go with emitter current will be simply defined as 1 plus alpha times of base current. You all know this one. When I will replace it in terms of base current defined, it will become 1 plus beta times of base current into 1 plus beta times of collector to base leakage current. That is how we are defining emitter current. This expression won't be changed, but this is in terms of beta for collector current, this is for emitter current. That's all. I hope you are just recapture மட்டும் பண்ணிக்கோங்க. That is enough. Next, let us discuss about a few more things about BJT configuration. இப்போ நம்ம BJT configuration அடுத்து வந்து I'm requesting you all kindly go through the characteristics of input output, because here நான் characteristics வரைஞ்சி நான் அதை explain பண்ண முடியாது, right? For that I have to explain how it is started, where it is started, எப்படி போகுது, எந்த region, எல்லாமே நம்ம define பண்ணணும், correct? So let me simply define the basics, right? I cannot go up with all the things here. So first of all, நமக்கு என்ன தெரியும் அப்படின்னா transistor வந்து two regionsல act ஆகும் basically. When we are, suppose if I will draw the curve between collector current versus VCB, transistor waveform வந்து observe பண்ணீங்கன்னா it will be like this. So here this region is called saturation region. That is called saturation region, and this region is called active region, right? In the below current oda value suppose இப்ப இந்த மாதிரிலாம் போகுது அப்படின்னா இந்த ரீஜனுக்கு பேர் நம்ம என்ன சொல்றோம் அப்படின்னா cut off region. That is called cut off region. Generally transistor will be activated எங்க நம்ம யூஸ் பண்ணோம் அப்படின்னா in active region. Transistor வந்து generally இங்க தான் வந்து அது என்ன act ஆகும், amplifier. Transistor will act as an amplifier in active region. That's why we are using always it. That's why transistor will be always operated in active region. Okay, active region க்கு ஒரு certain limit தான் இருக்கு. அந்த லிமிட் தாண்டி போனீங்கன்னா breakdown region will occur. So அந்த ரீஜனுக்குலாம் போக மாட்டாங்க, right? So that is some of the basics. So you please go through all the basics and waveforms characteristics. I cannot define all those things, just to remember. Okay, let us go with the next one, that is called DC load line characteristics of BJT. So DC load line வந்து நம்ம வரைஞ்சோம் அப்படின்னா BJT க்கு how it will look like. Let me draw the graph quickly. So that is the curve between collector current versus collector to emitter voltage. That curve will be like this. Okay, just now I saw that I have drawn the same curve, no? Yes. Here this region is called saturation region. This is called saturation region, and this region is called active region. This region is called breakdown region. That's all, right? So this is called what? Active region. This region is called active region. Now there will be a DC line between these two. Sorry guys, this is DC line, right? Fine, this is DC line. So this point will be VCC by RC. I hope I'm correct. And this is VCC, I know very well. இப்போ இந்த DC லைன்ல வந்து ஆக்சுவலா நம்ம என்ன பண்ணுவோம் அப்படின்னா some basics you have to remember. டிரான்சிஸ்டர் வந்து எப்போ வந்து ஆக்டிவ் ரீஜன்ல இருக்கும் அப்படின்னு நீங்க ப்ராப்ளம் சால்வ் பண்ணும்போது நியூமரிக்கல் கொஸ்டின்ஸ் வந்து இந்த பேசிக்ஸ் வந்து வச்சு கேட்பாங்க. ஃபர்ஸ்ட் வந்து டிரான்சிஸ்டர் when transistor will be in active region, in that case base current value must be less than that of collector saturation current divided by beta. Most important condition you have to check. First you have to calculate the collector saturation current. After calculating it, you should check. Saturation current will be given in your examination. நீங்க வந்து IC saturation by beta ஓட வேல்யூ வந்து பேஸை விட அதிகமா இருக்கா இல்லையா அப்படிங்கறத செக் பண்ணி பார்க்கணும். இந்த கண்டிஷன் சாட்டிஸ்ஃபை ஆனாதான் டிரான்சிஸ்டர் எந்த ரீஜன்ல இருக்கும்? ஆக்டிவ் ரீஜன்ல இருக்கும். இந்த கண்டிஷன் வச்சு क्वेश्चन கேட்பாங்க. That's why I am defining it. Opposite case, suppose sir base current oppositeல வந்துருச்சு sir, greater than IC set collector saturation current divided by beta sir. In that case transistor எந்த ரீஜனுக்கு போய்டும் அப்படினா it will be operated in saturation region. இந்த ரீஜன்ல இருக்கும். ஓகே, சோ ஆக்டிவ் ரீஜனுக்கு நீங்க டிரான்சிஸ்டர் வந்து கொண்டு வரணும் அப்படினா கண்டிப்பா என்ன இருக்கணும்? பேஸ் கரண்ட் must be less than that of collector saturation current divided by beta. That is most important formula. Okay, fine sir. One minute guys. Yes, next transistor வந்து saturation region போகும்போது என்ன ஆகும் அப்படினா the collector to emitter voltage வந்து will become equal to the value of collector to emitter saturation voltage. அதாவது டிரான்சிஸ்டர் சேச்சுரேட் ஆனதுக்கு அப்புறம் கலெக்டர் டு எமிட்டர்ல எவ்வளவு வோல்டேஜ் டிராப் ஆகுதோ that voltage will become considered as VCE when we are entering into saturation region. Similarly, this VCE value will be equal to VCC when we are in cutoff region. If we are in cutoff regionல actually collector current வந்து 0 ஆயிடும். அந்த டைம்ல VCE யும் VCC யும் ஈக்குவல் ஆயிடும். That is common case. Similarly, you will be requested to calculate the power dissipation. டிரான்சிஸ்டர்ல பவர் டிசிபேஷன் கேட்டாங்க அப்படின்னா எந்த வோல்டேஜையும் எந்த கரண்ட்டையும் மல்டிபிள் பண்ணணும் சார். தட் இஸ் தி டவுட்ஸ். If you are requested to calculate the power dissipation, go up with the collector current, collector to emitter voltage. Okay, that is the formula to obtain the power dissipation in our transistor. Okay, I hope you all are getting it. Apart from that, you have to understand few more basics. Let me define all those things. That is, when we are entering into a transistor bias circuits, bias stabilization is very important one. Let me give the general formula. இதை எப்படி கால்குலேட் பண்றது ஒவ்வொரு சர்க்யூட்க்கும் அப்படிங்கறத நம்ம கிளாஸ்ல நடத்திருக்கோம். வெளியில இருந்து வந்தவங்களும் நீங்க லெக்சர்ஸ் எல்லாம் பார்த்திருந்தீங்கன்னா உங்களுக்கு தெரிஞ்சிருக்கும். So I cannot define all those things, but this is important. எக்ஸாம்ல இதை தான் கேட்பாங்க. இருந்தாலும் இந்த ஃபார்முலால இருந்து நீங்க மத்த எல்லாத்தையும் கொண்டு வந்துடலாம். I hope you all know these things. So let me define. First of all, the changes in collector current will be defined as dou IC by dou ICO into del ICO. Second one, dou IC by dou VBE into del VBE plus dou IC by dou beta into del beta. அப்படின்னா மீனிங் என்ன? ஆக்சுவலா நம்மளோட ஒர்க் என்ன அப்படின்னா டிரான்சிஸ்டர் வந்து ஸ்டேபிளான ரீஜன்ல வந்து ஆப்ரேட் பண்ண வைக்கணும் அப்படின்னா கியூ பாயிண்ட் வந்து நீங்க ப்ராப்பரா மெயின்டைன் பண்ணணும். கியூ பாயிண்ட் அப்படின்னா தட் இஸ் VCE, IC பாயிண்ட். கலெக்டரோட கரண்ட்டுக்கும் கலெக்டர் எமிட்டர் வோல்டேஜுக்கும் நடுவில் அவங்க ரெண்டு பேரும் ஜாயின் பண்ணிட்டு வர நம்ம ஒரு பாயிண்ட் வரைப்போம் இல்லையா? தட் இஸ் கால்டு கியூ பாயிண்ட். அதாவது இப்ப நான் முன்னாடி கிராஃப்ல வரைஞ்சேன்ல, சீடர் திஸ் இஸ் கியூ பாயிண்ட். இந்த பாயிண்ட்டுக்கு மேல போனீங்கன்னா ஆக்டிவ் ரீஜன், இந்த பாயிண்ட்டுக்கு கீழே வந்தீங்கன்னா சேச்சுரேஷன் ரீஜன். ஸோ இந்த Q பாயிண்ட் வந்து நீங்க கரெக்டான இடத்துல ஃபிக்ஸ் பண்ணணும். நீங்க இதை தப்பான இடத்துல ஃபிக்ஸ் பண்ணிட்டீங்கன்னா சேச்சுரேஷன் ரீஜனுக்கு டிரான்சிஸ்டர் என்டர் ஆகிறதுக்கு வாய்ப்பு இருக்கு. ஸோ இன் ஆர்டர் டு ஸ்டெபிலைஸ் தி டிரான்சிஸ்டர் Q பாயிண்ட் வந்து கரெக்டான இடத்துல நீங்க ஃபிக்ஸ் பண்ணணும். அப்படி ஃபிக்ஸ் பண்ணலனா என்ன ஆகும்? ஆக்டிவ் ரீஜன்ல இருக்க டிரான்சிஸ்டர் மேபி அண்டர்கோயிங் டு சேச்சுரேஷன் ரீஜன். ஸோ திஸ் இஸ் வெரி இம்பார்ட்டன்ட். அப்ப இந்த Q பாயிண்ட்ல வந்து ஒரு டிரான்சிஸ்டர்ல வோல்டேஜ் வந்து ஃபிக்ஸட் ஆயிடும். Q பாயிண்ட் வந்து எப்ப அட்ஜஸ்ட் ஆகும் அப்படின்னா when there will be a changes in the value of collector current. collector current எப்பப்பெல்லாம் சேஞ்ச் ஆகும்? First one, collector current will change due to the value of ICO, or it will change due to the value of base to emitter voltage, that is diode voltage drop. It will also change due to the amplification factor, current amplification factor. So அப்ப இவங்க மூணு பேர், this is leakage current, collectorல enter ஆகிற leakage current. ஸோ அப்போ இவங்க மூணு பேராலும் என்ன ஆகும் அப்படின்னா கலெக்டர் கரண்ட்ல சேஞ்சஸ் வர வாய்ப்பு இருக்குதோ? ஓகே சார், லெட் மீ டிஃபைன் ஆல் தோஸ் திங்ஸ். இதுல இந்த டெல் ஐசி பை ஐசி நாட் நம்ம டிஃபைன் பண்றோம் இல்லையா, திஸ் இஸ் கால்டு கரண்ட் ஸ்டெபிலிட்டி ஃபேக்டர். வி ஆர் காலிங் இட் அஸ் கரண்ட் ஸ்டெபிலிட்டி ஃபேக்டர். The second term is there, right? Current with respect to voltage. This is called voltage stability factor. Voltage stability factor. Third term, IC by beta, that is amplification stability factor. Name எப்படி வச்சிருக்காங்கன்னு தெரியுதா? First current versus current. Variation in collector current with respect to current, that's why it is called current stability. Variation in current with respect to voltage, that's why it is called voltage stability. Variation in current with respect to amplification factor, that's why it is called amplification stability factor. Correct? I hope you all are getting it. Fine sir. So here இதுல வந்து 3 people இப்ப நம்ம பார்த்தோம் இல்லையா, இதுல வந்து which term is most significant term? இதுல most significant term யார் அப்படின்னு கேட்டீங்கன்னா current stability factor. So we have been discussed about 3 people, right? Current stability factor, voltage stability factor, amplification stability factor. Out of these 3 people, the most highly sensitive, significant, reasonable value நம்ம டிரான்சிஸ்டர் அஃபெக்ட் பண்ணது யாருன்னு கேட்டீங்கன்னா கரண்ட் ஸ்டெபிலிட்டி ஃபேக்டர் தான் வந்து மோஸ்ட்லி அஃபெக்ட் பண்ணும். அப்ப நம்ம என்ன பண்ணணும்னா we can neglect the second 2 terms. We need to keep our attention with the first term, that is current stability factor. அப்ப current stability factor வந்து நம்ம எப்படி சொல்லிருந்தோம்? Variation in collector current with respect to ICO. கரெக்டா சார்? எஸ். So the thing is, ஐடியலா சொல்லணும் அப்படின்னா இதோட வேல்யூ வந்து கண்டிப்பா 1 வரணும். practically சொல்லணும் அப்படின்னா இதோட வேல்யூ வந்து less than 20 இருக்கணும் அட்லீஸ்ட். this is practical case. ஏன்னா அவ்வளவு வேல்யூ வந்துரும். practically this value should be less than 20. ideally it is 1. ideally it is 1 only. Fine sir. What is the alternative value? Now we are entering into the most important region. இங்க தான் क्वेश्चन உங்களுக்கு கேட்பாங்க. ஆக்சுவலா இந்த ஃபேக்டர் உங்களுக்கு கண்டுபிடிக்க சொல்லுவாங்க. என்ன ஃபேக்டர்? கரண்ட் ஸ்டெபிலிட்டி ஃபேக்டர் உங்களுக்கு கண்டுபிடிக்க சொல்லுவாங்க. So current stability factor எப்படி கண்டுபிடிக்கிறது? For that the formula, current stability factor means variation in collector current with respect to, that is del IC by del ICO. இது எப்படி நீங்க calculate பண்ணணும் அப்படின்னா the formula is 1 plus beta upon 1 minus beta times of variation in base current divided by collector current. Okay, that is variation in base current divided by variation in collector current. This is the formula that we are using standardly in order to obtain the current stability factor. Don't forget, very important formula. Okay, yes, I hope you all are getting it. அதே மாதிரி என்ன ஆகும் அப்படின்னா இதோட வேல்யூ வந்து நம்ம டிரான்சிஸ்டர்ல நிறைய கான்ஃபிகரேஷன் பார்த்திருப்போம். வோல்டேஜ் டிவைடட் பயாஸ் கான்ஃபிகரேஷன், கலெக்டர் ஃபீட்பேக் பயாஸ் கான்ஃபிகரேஷன், ஃபிக்ஸட் பயாஸ் கான்ஃபிகரேஷன், இந்த மாதிரி நிறைய கான்ஃபிகரேஷன் இருக்கும். அதுல S ஓட வேல்யூ வந்து in case of fixed bias configuration it will be equal to 1 plus beta. Actually நம்ம ஒவ்வொரு இதுக்கும் நான் இதை டிஃபைன் பண்ணிருப்பேன், kindly go through it, but this is little bit important, that's why I am defining it here. This is for fixed bias configuration. remaining எல்லாத்துக்கும் நம்ம எப்படி பண்ணணும் இதை அப்படின்றத நான் derive பண்ணிருப்பேன். kindly go through the lectures. Okay, so S equal to 1 plus beta. This value is very large. beta value usually ரொம்ப அதிகமா தான் இருக்கும். So fixed bias configurationல current stability factor will become very large, very large. So system வந்து என்ன ஆகும் அப்படின்னா it will be highly stable. Here it is highly stable. That's all. I hope you all are understanding the basics. Okay, so apart from that, what you have to do is next நம்ம transistor யூஸ் பண்ணி how to calculate the voltage gain, current gain, இதெல்லாத்தையும் நம்ம எப்படி calculate பண்ணோம், output voltage எப்படி calculate பண்ணோம், input impedance எப்படி calculate பண்ணோம். That is when BJT is acting as an amplifier. நம்ம என்ன சொன்னோம், BJT வந்து நம்ம மொத்தமா 4 region பார்த்தோம். Active region, reverse active region, saturation region, cutoff region. But in which region most preferably our transistor will be operated? Transistor will be operated only in what? Active region. Because in active region only transistor can act as a amplifier. Right. So in the next lecture we will see the amplifier operations. அதாவது ஒரு டிரான்சிஸ்டர் வந்து நம்ம ஆம்பிளிஃபையரா ஆக்ட் பண்ணும்போது ஒரு காமன் எமிட்டர் ஆம்பிளிஃபையர் எடுத்துக்கிட்டாலோ இல்ல காமன் கலெக்டர் ஆம்பிளிஃபையர் எடுத்துக்கிட்டாலோ அதுல வந்து கெயின்ஸ் எல்லாம் எப்படி வருது. I am just shortly revising it. I cannot derive all those things. I will give you in short. I will explain and then we will move on to the MOSFET. Right, metal oxide semiconductor field effect transistor. So அதுக்குள்ள போயிட்டு அது எப்படி ஆப்ரேட் ஆகுது, அது எப்படி ஆப்ரேட் பண்றது, அதுல கரண்ட்ல எப்படி கால்குலேட் பண்றது, everything we will see one by one. With this, let's wind up the today lecture. Right, if you have any doubts you can connect with me through WhatsApp. Okay, fine. So with this, let's wind up the